Okay, good day. So this recorded lecture is a continuation from the last topic, statics for engineering mechanics. So we will continue, so the succeeding topics under this recorded video. Okay, so let me share again. Okay, so the previously left. Okay, so topic. Okay, so we are now in equilibrium, for coplanar non-concurrent force system. Okay, so we have this condition, okay, for uh, coplanar non-concurrent force system under equilibrium. Okay, so we have here the two conditions. The first one is the resultant force, or the summation of the forces in a system must be zero. Okay. The second one is that the summation also, of the moment uh, in a system must also be zero. Okay. So take note that we cannot apply Lami's theorem in this setup because as we defined, so non-concurrent force system does not have a force or does not have a point uh, of intersection. So we just use the following conditions, as stated a while ago, to analyze the uh, concept of coplanar non-concurrent force system under equilibrium. So again, the summation of the forces, okay, so is equal to zero, and the summation, of the moment in the system must also be zero. Okay, and then we have here three. Okay, so three problems. Okay, so for the topic, so we will proceed right away. Okay, so for example, number 8. So you have there two men left lift, so the ends of a 20-feet beam weighing 200 pounds onto their shoulders. Okay, so both men are of the same height, so that the beam is carried horizontally. So, but one is much stronger of the two and wishes to bear 50% more of the weight than his mate. So how far from the end of the beam should he put his shoulder? Okay, so kindly gather the data, so before we proceed. Okay, uh, okay, let me share. Okay, so according to the setup or according to the problem, okay, okay, so according to the problem, okay, so there is a beam. Okay, so we can have this as the beam. So the beam is 20 feet long. Okay, so that's 20 feet. Okay, and the weight. Okay, so the weight of the beam is given to be 200 pounds. Okay, so this would be the weight of the beam, which is equivalent to 200 pounds. Okay, so take note the weight of the beam will concentrate now at the centroid of the beam, which is at the center now, of course, the center of the beam. And then also given one of the two men, so uh, he have or he has to carry the beam or part of the beam, at the end. Okay, so let us say this would be the force exerted by uh, one of them. Okay, so let us say force F, and the other, since according to the problem, the other man, no, is stronger as compared, no, to the first man, then he has to carry 50% more weight. Okay, so the second man will have to put, okay, so the part of the beam, okay, so a distance d, no, so assuming this would be point A, so the second man will have to put, okay, so part of the beam a distance d away from the other end, no, so let us say this would be distance d, and then the force exerted by that man is 1.5 times the force exerted by the other. Okay, so this would be the free body diagram for problem number 8. Okay, so we then say that the summation of the forces is equal to 0. So since we only have y component, okay, so y component of the force, because all of them are oriented vertically. Okay, so we then say that 200, okay, so minus f minus, okay, that's negative 200 plus f plus 1.5 f, so that would be 0. Okay, so we can then say, no, that's 200, that's equivalent to 2.5 f, and then we can calculate f to be 80 pounds. Okay, so remember, this is the first condition, no? So for coplanar non-concurrent force system, okay, so the summation of the forces was equal to 0. Okay, and then the second one, the problem is asking for the distance d, no? So not the magnitude of the force exerted by the first man or the second man. Okay, so but the distance d. Okay, so to calculate, we then make use of the second condition, no? That is the summation of moment in a system is 0. Okay, so for simplicity, to calculate d directly, okay, so we take, no, summation of moment at point A that is equal to 0. So this would be our reference point, point A, and then we sum up all the moments. No? So again, moment is equal to force multiplied by the perpendicular distance d. Okay, so and also since the weight is concentrated at the centroid, so then the length from this end to the middle is 10, and might as well 10 feet also in the side. Okay, so we take moment. Okay, so 200 now with respect to point A, so the 200 pounds will create negative moment because it produces counterclockwise rotation. Okay, so that's negative 200, so multiplied by 10. Okay, so plus, so both of the two forces now will create clockwise rotation, so that means the moment produced by each is positive. So that would be f multiplied by the perpendicular distance to point A, that is 20, plus 1.5 f multiplied by distance d. So substituting the value of f, no, so we can calculate d. Sorry, this would be equal to 0. So d then can be calculated as 3.83 feet. Okay, so the second man will have to put part of the beam 3.33 feet away from the other end. Okay, so for the condition to be met, no, so the condition is that you must carry 50% more of the total weight into his shoulder. Okay, so let us try to look at if we have the answer, no, from the choices. Okay, so here it is, no? So letter C, that's 3.33 feet. Okay, and then we move to the second problem, second sample problem. Okay, so we have here in example number 9. So we have there a uniform wooden beam of length 20 feet and weight 200 pounds. No, so that is lying on a horizontal floor. So a carpenter raises one end of it, okay, until the beam is inclined at 30 degrees to the horizontal. Okay, so he maintains it in this position by exerting a force at right angles to the beam while he waits for his mate to arrive to lift the other end. So what is the magnitude of the force he exerts? Okay, so so again, we need to draw, no, the free body diagram for example number 9 in order for us to calculate, no, so what is being asked, no, the problem. Okay, so let me go back to the whiteboard screen. Okay, so here we go. So for problem number 9, so initially, so the beam is situated horizontally, this one. So this would be 20 feet beam, and the weight given to be 200 pounds. So the carpenter, no? So the carpenter decided to raise one end of the beam. Okay, so such a way that the beam will look like this one. Okay, so with respect to the horizontal, the beam now makes an angle with 30 degrees, no, with respect to the horizontal. So might as well, according to the problem, the carpenter, no, so lift the other end, but the force exerted is perpendicular with respect to the beam. So we need to say the force exerted by the carpenter, I mean, no, so carpenter. So this would be the force exerted by the carpenter. So in order for the beam, okay, to be inclined at 30-degree angle, so it was stated in there that he maintains it in this position. So that means the system is under equilibrium. Okay, and might as well do not forget to add the weight. No, so the weight of the beam will always be situated or will always be pointing downward, of course, vertically, 200 pounds. Okay, so also since the beam and the floor also is in contact, we can say that the floor and the beam, no, so has this what we so called reaction force, no. So this would be the reaction, so force, the vertical reaction force, no, between the beam and the floor. So we can call this one Py, and of course this one to prevent it from sliding. So there is a reaction force. So we term this one Px, this one. Okay. So what the problem wants us to uh, identify is the amount, no, or the magnitude of force F. Okay. So if you try to look at, there are three unknown quantities or unknown variables, F, Px, and Py. Okay, so how are we going to make an approach, no, with the problem? Okay, so when taking moment, okay, so always remember when taking moment, it is best not to make the or to take the moment, no, so or the reference point uh, at a point wherein there are many unknown forces. So because the forces that is concentrated now at that point will not be considered, no, in calculating the moment, because the moment of a force with respect to the point where it concentrates is zero. So let us say that this would be point A, and then when we do summation of moment at point A, so that is equal to zero, right? Okay, so moment then is defined, no, as the force multiplied by the perpendicular distance from the force to the reference point. Okay, so if you take a look at the 200 pounds will create clockwise rotation, the force F will create counterclockwise rotation. So if you try to look at the 200 pounds, no, is or will have a distance of shall we say D. The vertical distance, no, of the 200 pounds to point A is denoted by D, whereas point F or force F, no, so to point A is 20 feet, no, so because the length of the beam is 20 feet. So we then say that the moment, okay, so that's 200 multiplied by D, okay, so 200 multiplied by the distance D minus F multiplied by 20, that is equal to 0. So as you can see, since we took the moment, no, at point A, Px and Py, okay, the moment of Px and Py is 0. Okay, so, or the moment, no, so the moment produced by Px and Py at point A is 0. Okay, so now if you take, no, so the reference point somewhere, shall we say you make the reference point in this position, then you have to consider Px and Py, no? So to eliminate the variables, then we create a reference point. The best way is to create, no, so a reference point to a point where there are more forces concentrating, no, at that particular point. So you can see, so D then is, or D can be calculated as, no, so this would be, we know that this is 10 feet. So this would be also 10 feet. Okay, so and then we can have, okay, this triangle. So this would be D, so 30 degrees, 10 feet. So D can be calculated as 10 cosine of 30. Okay, so we try to substitute. So we have there 200 times 10 cosine of 30 degrees. So that is equal to F multiplied by 20. So calculating for F, then we have, okay, 200 times 10 cosine of 30 divided by 20. So we have there a force of 86.6 pounds. Okay, so that would be 86.6 pounds, no, for problem number 9. I will try to take a look at if we have the 86.6 pounds, no, from the choices. So we have the, okay, that's letter D, no, 86.6 pounds. Okay, and the last example, no, so the last example for equilibrium, no, under coplanar non-concurrent force system is shown, no, in example number 10. Okay, so for example number 10, so still we have a beam, okay, subjected to a distributed load as shown. Okay, so this is an example of a distributed load, no, so as shown, So, and is simply supported at both ends. Okay. So determine the reactions at support A. No? So we are asked to calculate. So the reaction, no? So at support A, this one. Okay. So take note. So we have this distributed load. So we have here 100 pounds per foot, and then we also have here 300 pounds per foot. Okay. So how do we analyze distributed load? No? So we go to okay. Uh, so we have, okay, in problem number 9, 10. Okay. So in problem number 10, so we have there a simply supported beam. This one. So this would be the beam. So it actually carries two loads. No? So distributed load. So we can consider that as this one. So okay. So the distribution is 100 pound per foot. Might as well an additional load. Okay, so this one. Okay, so I separated the two, no, for us to analyze them uh, simpler. No? So the distribution is, since we have already 100 pound per foot, so this one would be 200 pound per foot. So although the problem states no, that it's 300 pound per foot, but that is with reference no, from the beam. Okay. So then we have the support A, B, and then we also have A. Okay. So take note for distributed load. Okay. So we'll have to take note of this. No. So for uniformly distributed load, so with load distribution like this, so assuming that the uh, force per unit length is given with omega, okay, and then the length of the beam is L, so it can be replaced, no? Okay, it can be replaced with a single force, no? So whose magnitude is the product of omega and L, okay? So instead of 100 pound per foot for the entire length, so uh, the entire load distribution can be replaced with a single concentrated load whose magnitude is multiplied product of the uh, force per unit length multiplied by the entire length of the beam. Okay. So also take note that this force will concentrate at the centroid. No? So we have here L over 2 and of course the other one L over 2 also. Okay. For the triangular load distribution, okay, so for example, we have here a triangular load distribution. Okay, so we'll try to erase. Okay, so for triangular load distribution, so suppose you have here a triangular load distribution. So given with force per unit length omega, okay, and the length of the beam, shall we say, is L. So the triangular load distribution can be replaced with a single concentrated load. No? So it can be replaced with a single concentrated load whose value is equal to, okay? So you have there the equivalent single concentrated load situated here. So this force is equal to 1/2 multiplied by omega L. So it will concentrate at a distance. Okay, so this would be L over 3. And then the distance here is 2L over 3. Okay, so meaning to say we can replace this distributed load, no? So the rectangular distribution and the triangular distribution, we can replace them with single concentrated load, no? So in such a way that the free body diagram can be reduced to, okay, so this is the beam, okay, so it will have a support B and the support also at the other end A, okay. So try to consider first, no? The length of the beam is 18 feet, okay, 18 feet. Okay, so for the rectangular load distribution, so the equivalent concentrated load is at the center. So this would be labeled F1. Okay. For the triangular load distribution, so it will be, so the distance here is 9 feet. Okay, and might as well the other end. So that would be 9 feet. For the rectangular load distribution, so we can have it here. Okay, so this would be F2. Okay, so this is for the rectangular load distribution. This one is for the triangular load distribution. So this would be, as you can see, the distance here is total length divided by 3. So that would be 6, right? So this would be 6 feet and this would be 3 feet. Okay, so it will have a total length, so of 18 feet. So L over 3, and then the distance from this point to the other end is 2L over 3. So 2 times 18 divided by 3, that makes it 12. Okay, so this would be the final free body diagram of the given simply supported beam. Okay, so we'll try to erase this one. Okay, so to give us room for the calculation. Okay, so now we proceed to the solution, no? Okay, so we begin with calculating for F1, no? So F1 would be equal to, no? So 100 pounds per foot multiplied by 18 feet. So that would be 180 pounds. F2, on the other hand, would be 1/2 multiplied by, so that's 200 pounds per foot multiplied by 18. So that would be, do not use 300 pounds per foot because 100 is part of the rectangular load distribution, no? So 0.5 times 200 times 18. 1,800. By the way, this is 1,800. And okay, and this one is also equal to 1,800 pounds. Okay, so now we have two unknowns. Actually, we have reaction B and reaction A. So how are we going to identify, no? So the value of A. So we take the reference point at shall we say, point B. Okay, so the reason why is to eliminate the moment effect of reaction B. So we'll have to select point B as our reference point. Okay, then we say summation of moment at point B, so that is equal to 0. Okay, so F1 and F2 creates positive moment, A creates negative moment. Okay, so that would be negative A multiplied by the total length, 18, no? A multiplied by the total length. So plus F1, so that's 1,800 multiplied by 9, and plus F2, 1,800 multiplied by 12, so that would be 0. So calculating for A, so this would be the reaction for A, no? So that's A is equal to 2,100 pounds. Okay, so we have here the answer, no? 2,100 pounds. So let us check if we have that choice, no? Number from the given choices. So here it is, no? So that's letter A, that's 2,100 pounds. Okay, and then we proceed, no, to the next topic. Okay, so the next topic would be the friction force. Okay, so first we define, no, so what's a friction, no? So friction is the resistance to motion, no? So the direction of the friction is always opposite, no, to the, not to the applied force, but it is opposite, not to the displacement, no, or opposite to the movement of the particular uh, object, no, or particular body. So if the body is stationary, then the friction is opposite to the impending motion, no, of the body. So, and then we can classify, no, so friction. So into three, we have the static friction. Okay, so that is for uh, two stationary, no, a force between two stationary surfaces. Okay, and then we have the kinetic friction. Okay, so if the body is moving, no, and then the rolling friction, no, so if the body involves rotational motion. Okay, so we may say, no, we may say that uh, the value, no, the value of the friction force is equal to the coefficient of friction multiplied by the normal force. Okay, now the normal force, okay, so weight, before we go to the normal force, so take note that the weight of the object, or weight of the body, is always uh, situated or positioned vertically. No, so regardless the object is situated in a horizontal plane, or it is inclined like this one, so the weight is always okay. So the weight is always situated or positioned vertically downward. But the normal force, okay, so the normal force is always not perpendicular. To take note, it's always perpendicular to the surface. No? So, uh, for example, if the object is placed now in a horizontal manner like this one, so the normal force will be pointing downward, I mean upward, not vertically. But if the object, no, so is placed, for example, in this case, so the plane is inclined, so the weight is positioned downward, vertically, whereas the normal force, no, is positioned. So take note, it's always perpendicular to the surface. No, so uh, the one that dictates, no, the position of the normal force is not the uh, or the one that will dictate, no, the position of the normal force is the surface actually, no. So it will always be positioned perpendicular to the given surface. Okay, so and then we have the coefficient of friction, no? So it's either given or it's either the one that is being asked, no? And then the friction force, no? So that is equivalent to the coefficient of friction multiplied by the normal force. Okay, so we have three. Okay, so three examples. Okay, so for the topic friction force, no. Okay, so we'll try to analyze them one by one. Okay, so okay, so we have in problem example number 11. So you have there a 1,200-pound sled is pulled. Okay, so it's along a horizontal surface, no? So at a uniform speed, okay, by means of a rope, no? So that makes an angle of 30 degrees above the horizontal. Okay, so if the tension in the rope is 100 pounds, what is the coefficient of friction? Okay, so we are being asked, no? So to calculate the coefficient of friction. So in example number 11, okay, so try to draw, no, the free body diagram of the setup. Okay, so we are now in problem number 11. So this would be the sled, no? So the weight of the sled is 1,200 pounds, no? So this is the weight, no? So will always be vertical, no? Pointing downwards, okay? And then according to the problem, the okay, so okay, so okay, so for uh, it's actually in the sled, no, it's actually in a horizontal plane, no? So but the okay, but the force that is being applied is inclined, no? So it's not the surface that is being inclined, no? So that would be sled. And then um, this would be the weight, no? Of course, the weight of the sled is 200 pounds. So this would be the weight. And as per the problem, it's the force, no, that's being applied. So it makes an angle with 30 degrees, no? So with respect to the horizontal. So it's not the surface that makes 30 degrees, but the applied force. Okay, and then the applied force, no, is equal to 100 pounds. Okay, so this would be 100 pounds. So the motion, of course, no, the motion of the sled, of course, is going in this direction. So we then say, no, that the friction force will oppose, no, the motion of the sled. No? So this would be the friction force, F, and we also have the normal force. No? So the normal force is perpendicular to the surface. No? So, okay. So we didn't say, no, we didn't say that if we do summation of not moment, but if we do summation of forces along y, so that is equal to 0. Okay, so the weight is equal to the normal force, no? So which is equivalent to, okay, not okay, not equal, no, because we have there the force, no. So we didn't say, let me, okay, erase first. Okay, so we didn't say, no, that the force. Okay, so we forgot to include the force now in our analysis. So the force will have its component, x component, and also it has the y component, no? Fy. So the force component, no, so is given as uh, follows, no? Fx is equal to 100 cosine of 30 degrees. Okay, and then Fy would be 100 sine of 30 degrees. Okay, so if we do summation of forces, no, so along y, so that makes it weight. Okay, so that is equal to the normal force plus the force component along y. Okay, so we have there the value 200, that is equal to normal force plus 100 sine of 30. So calculating for n, so it will give us a value of 200 plus or minus 100 sine of 30. That makes it 150 pounds. Okay. And if we do summation of forces, no, so along x, so that would be also equal to 0. So that makes it Fx, that is equal to the friction force, no? Okay, so Fx would be equal to 100 cosine of 30, no? That is equal to the friction force, which is equal to 86.6 pounds. Okay, so we are being asked to calculate for the coefficient of friction, no? So the coefficient of friction is given by, no? So if you try to recall, the formula for the friction force is equal to mu n. Okay, so we have there 86.6 pounds, so that is equal to the coefficient of friction multiplied by the normal force 150. So the coefficient of friction is equal to, okay, that's equivalent to 0.577. Okay, so try to take a look at the coefficient of friction, that is 0. Okay, 1,200 pounds, 100 pounds. Let me check now. So 1,200. Okay. Okay, sorry, we're using a different value, no, for the weight, no. So it's 1,200 pounds, not 200. Okay, so this would be 1,200, and this would be 1,200. So we'll just erase, no. So the normal force is equivalent to, okay, so instead of 1,200, so, or 1,200, no, we use 200, no? So anyway, we'll recalculate. The normal force is 1,150 pounds. Okay, so this would be 1,150 pounds. So we just divide 86.6 by 1,150. No? So that's okay. So the value is 0.0753. Okay, so check no, if we have that 0.0753 no, from the choices. Okay, there it is. No? So in letter C, that's 0.0753. Okay, so, and then we move no, to the next example. That is example number 12. No? So still about friction force. Okay, so in example number 12, so we have there a body weighing 350 pounds, no? So on a plane inclined. So this time the plane is inclined 30 degrees now with the horizontal. So the angle of static friction between the body and the plane is 15 degrees, no? So uh, we'll try to um, explain later, no? So what the angle of static friction means, no? So that is 15 degrees. So what horizontal force P, okay, is necessary to hold the body, no, from sliding down the plane, okay? So, okay, we'll try to draw, no, the free body diagram of this uh, problem. So this would be for problem number 11. Okay, so number 12. Okay, so in problem number 12, so we have um, the reference, no? So the horizontal reference line, and then the surface, no? So it's inclined, no? According to the problem, it is inclined 30 degrees no, with respect to the horizontal, so that is 30 degrees. And then you have there a body weighing 350 pounds, no? So the body is, let's say this is the body mentioned, no? So it could be a box. Okay, so the weight is given to be 350 pounds. Okay, so the problem is asking for uh, what would be the horizontal force P, no? So needed to be applied no, to the body in order for the body to uh, okay, what horizontal force P no, so is necessary to hold the body. So meaning to say, um, okay, meaning to say that a horizontal force P is needed to hold the body at rest. No? So without the force P, so the body will intend to slide down. So therefore, the impending motion of the body is in this direction. No? So this would be to the motion no, of the body. So, but according to the problem, the force to be applied must be horizontal. So this would be the horizontal force P. Okay. So if we try to take a look, So there are these forces that also exist, no, in the given system. Number one, so we have there the normal force, so which is perpendicular to the surface, and then the other one we have the friction force also, no? So now the friction force is not opposite to the applied force, no? So but it is opposite to the impending motion of the body, or opposite to the direction of the movement, no, of the body. So you have there the four forces, no? Okay. So we'll try to have, okay, so a better view, no, of the free body diagram. So okay, so this would be the inclined plane. So this would be the body force, no? So and then uh, we'll try to, okay, so we'll try to make the uh, okay, we'll try to make the horizontal plane. I mean, we'll try to make the inclined plane as our imaginary x-axis. Okay, so such that we can also set this one, okay, as our imaginary y-axis. No? So, so we have here the friction force F, and we also have here the normal force N. Okay, so for the weight, okay, so the weight will have its component, no? So, so take note that this angle here is equal to 30 degrees. Okay, so we can draw a triangle, no? So for we denote this one to be WX, and then this would be WY. So if you try to look at, this would be the orientation. So you have there the weight, and then the components, the WX, WY, and then the weight. Okay, so this is 60 degrees. So this one is 90, so therefore this is 30 degrees, no? So that would be 30 degrees. So we then say that WX is equal to W sine of 30. WY on the other hand is W cosine of 30. Okay. So for force P, okay, try to take a look at force P. So force P will also have its Y component, so Py, and it will also have its X component, so shall we say Px. Okay. So the angle, okay, so that's Px and Py. No? So take note, uh, P is horizontal, no? Horizontally oriented. I mean oriented horizontally, no? So we can have the force P. Okay, so this would be, okay, so we can have the force P. Okay, and then we have here the force Py, and then we have there the force Px. So this would be Py, and then this could be Px, and then this would be P. Okay, so now if this is 30 degrees, so So if this is 30 degrees, then the angle here, okay, so let's use another color. So then the angle here is also 30 degrees, no? Okay. And then the angle here is also 30 degrees, right? So therefore, this is 30 degrees, okay? So if you try to take a look at this one, okay, so going back in your trigonometry, so Px would be equal to P, so that would be the adjacent side, no? P cosine of 30. And Py would be P sine of 30. Okay? So such that we have these forces, no, in our free body diagram. So we have here Wy and another one. So this would be Wx. So a component here. So that would be Px. And another component here that would be Py. Okay. So if we do summation of forces, no? So if we do summation of forces along x, so that would be 0. So what are the forces along x? No, so that would be, we have uh, Wx. Okay, so that is equal to Px plus F. Okay, the friction force. No, so that is Wx equals to Px plus F. No, so this would be 350 sine of 30. That is Px. So P cosine of 30. So plus the coefficient of friction F. Okay. So we do summation of forces along Y. No? So that is also equal to 0. Okay. So for Y component, so we have the following. No? So Wy plus Py. So that is equal to the normal force. No? Okay. So we know that the normal force. No? So the normal force is equal to, or the friction force. No? Okay. So we know that the friction force is equal to mu n. So are we given mu? So according to the problem, okay, let me show you the given problem. So according to the problem, the angle of static friction between the body and the plane is 15 degrees. No? So that means that the coefficient of friction, no? So mu, so that is equivalent to tangent of the angle between the body and the static friction. So that would be tangent of theta. Okay, so this one. So meaning to say mu is already given in the problem. Okay, so we calculate. No? So we go back to the whiteboard presentation. Okay, Wy is plus Py. So Wy is 350 cosine of 30. So Py is P sine of 30, while N, okay, so that is the friction force divided by tangent of 15. Okay, so if you can see, we have two equations, no? Two equations with two unknowns. That's P and F. Okay, so I believe you have your calculator, so you can type directly, no? So uh, go to equation mode, no, in your calculator, and then okay, type the equations, no? So accordingly, and solve for the unknown. Okay. So before that, you need to rearrange, no? So the equation is such that we have this one, no? Equation 1, so that's P cosine of 30 plus F. So that is equal to 350 sine of 30 degrees. No? So also equation 2 can be written as P. So the format must be followed, P, F, and then the constant. No? So that would be P sine of 30, okay, minus F. Okay, so that's F multiplied by 1 over tangent 10. Okay, so that is equal to negative 350 cosine of 30. So such that we have this unknown P and F, P and F, and then on the right side, so the constant values. So go to your equation mode, no? So select the function in your calculator which can solve the two equations by two unknowns, no? Of course, make sure that your calculator is in radian mode. Okay, so and then we have the sine of 30 negative 1 divided by tangent 15 negative 350 times cosine of 30. So this will give us P with a value of 93.78. Okay, and then the friction force also at 93.78. Okay, that is based from the answer, no, from the calculator. So we'll just okay, we'll try to see if we have the value 93.78 now from the choices. Okay, so let me share. So the value that is being asked is the force P, no? So we have here letter A, 94 pounds, no? So 93.78. So that's rounded up to the nearest full number, which is 94. Okay, so that's letter A. Okay, and then we proceed, no? So to the next, no? So next example, no? Example number 13. Okay, so okay, so in okay, so in example number 13, so we have here the uh okay, number 13, no? So we have here a 25 feet ladder rest, no? So rest against frictionless wall. So with the foot of the ladder inclined at 53 degrees from the floor, the center of gravity of the ladder is 10 feet from the foot of the ladder. Okay, so if the ladder weighs 80 pounds, find the coefficient of friction between the foot of the ladder and the floor. Okay, so it is stated here that the ladder, no, so the ladder is leaning against the wall, and then the other end is on the floor. So, but the wall is frictionless. Okay, so the the center of gravity of the ladder is 10 feet, no, from the foot of the ladder. And then the ladder weighs 80 pounds. So meaning to say the weight, no, will concentrate at the center of gravity now of the ladder, which is, according to the problem, 10 feet now from the foot of the ladder. Okay, um, so we are being asked, no, to calculate the coefficient of friction between the foot of the ladder and the floor. Okay, so let us go to the whiteboard. Okay, so for this would be for problem number 13. Okay, so according to problem number 13, so you have there the wall and the floor. No? So, and then you have there the ladder. Okay, so the ladder is 25 feet. No? So according to the problem, 25 feet. And the weight of the ladder, no, so is concentrated at the center of gravity, centroid, no, so which is 10 feet away, no, from the foot of the ladder. So that's given in the problem. So 10 feet, and then the wall is frictionless, no, so this one. So there is only the what we so called normal force, no, N1. So the supposed reaction is that the ladder will tend to slide downwards, no? But then since the friction, it's frictionless, okay, so that would be F2. So F2 is equal to 0. So why? Because it's given as frictionless, no? So the supposed to be motion is the ladder will tend to slide downwards, and this one the ladder will tend to move away, no? So, but in the floor, okay, so in the floor, no, so we have the normal force, no, shall we say N2, and of course there is the friction force, no, that exists, which is opposite to the impending motion, shall we say F2, F1. Okay, this would be F1 and N1, and we denote this one to be N2. Okay. So we are being asked, no, to calculate the friction force, no, uh, friction force, no, at the uh, between the ladder and the floor. Okay, so this is inclined at 53 degrees, no? So as given. Okay, so how are we going to solve this one, no? So okay. So we begin with, no, so the analysis, no, our objective is to first find F1 and N1, no. So if we have F1 and N1, then we can calculate for the coefficient of friction. So it is because F1 is equal to mu1 multiplied by N1. Okay, so finding F1 and N1, so would be our task in order for us to calculate for mu1. Okay, so but the problem is how are we going to calculate, no? Okay, so uh, we didn't say, no. So summation of forces, no. So we do say summation of forces along y that is equal to 0. Okay, so the forces, no. So let's say this would be our x-axis, And then this would be the y-axis, no? So summation of forces along y, so that would be 0. So weight is equal to N1. Okay. So the weight of the ladder is 80 pounds, no? So that would be 80, that is equal to N1. So we have already the value for N1. Okay. And then we do summation of forces, no? If we do summation of forces along x, so that would be 0. Okay. So we have here F1 that would be equal to N2. So N2 is unknown, F1 is also unknown. No? So we cannot use the value for, or we cannot make use of this equation because N2 is also unknown. However, we can make this one as our reference point. No? So shall we say this would be point A, but then we say that the summation, no? Okay, we say that the summation of moment at point A is equal to 0. Okay, so again, moment is equal to the force multiplied by the perpendicular distance. No? So this is point A. So we need to find the perpendicular distance. No, this one. So this is D1. So and might as well this distance also. Okay. So this would be D2 and might as well this distance also D3. Okay. So with respect to A, the weight will okay, before that one, we'll try to find D1, D2, and D3 first, no? So if you try to look at this triangle here, this one, so this is 53 degrees also, no? So you have there 53 degrees, no? Then this would be D1, and then this would be 15 feet, no? So since this is 10, so D1 can be calculated as 15 cosine of 53. Okay. Dito, on the other hand, can be calculated. No? So this D2, so the total length is 25. No? So that's 25 cosine of 53. And then D3 can be calculated, no, looking at this triangle, the big one. Okay, so this is the opposite of the included angle 53 degrees. So then that would be 25 sine of 53. Okay, so going back to the moment equation, now the weight will create now a negative moment because it produces a rotation of counterclockwise. Now, so that's negative uh, weight is 80 multiplied by d1, now the perpendicular distance, the d1, that's 15 cosine of 53 degrees. No? So whereas the force N1 will create a positive moment because with respect to point A, N1 will create this rotation, no? Clockwise rotation. So you have the N1, so multiplied with D2, no? So D2 is 25 cosine of 53 degrees, no? Whereas F2, no? Try to take a look at F2. F2 will create with respect to point A, so it creates this rotation. So that means F2 is or will create negative moment, no? So F2 multiplied by 25 sine of 53. This would be equal to 0. Okay, so N1 is already given to be 80, no? So we can calculate F2, no? So F2 then can be calculated as, so just substitute the value of N1, so that's negative, okay, uh, 80 times 15 cosine of 53. Okay, and then uh, minus 80 times 25 cosine of 53. Negative divided by negative 25 times sine of 53. F2 then is equal to 24.11 pounds. So, I'm sorry, this is F1, not F2. No? So, F1, uh, mu1, no? So, the coefficient of friction can be calculated by, so 24.11 divided by N1, no? 80. So, okay, divided by 80. So, we have here 0.3 as our coefficient of friction. Okay, so we'll try to take a look if we have the 0.3 value. Okay, so that's, there it is, no, in letter D. No, so we have uh, the coefficient of friction between the foot of the ladder and the floor to be 0.3. Okay, so okay, so the next topic, no, so still this is about friction, but this involves, no, so belt friction. So as you can see, okay, so we can illustrate this one, no, in some heavy lifting applications now, wherein uh, the workers uses rope, no, to lift a heavy object, no. So okay, so for belt friction, so we have this formula, no. Okay, so T2, so this is the tight side, no? So this is where the heavy uh, object, no, is being attached. T1, so this is the slack side, no? So this is where the, for example, this is where the workers they pull, no? So the T1 side, no? So in order to uh, raise, no, so the object, no, so which is connected to the T2 side. Okay, so beta on the other hand is the angle of contact between the rope, no, or belt, and the roller. So if the belt is wrapped around the rope, no, so then beta is equal to 360 degrees, no. So usually in heavy lifting applications, no? So usually the workers tends to wound the rope, no? So around the belt, I mean around the roller. So a number of turns, no? So each turn constitutes 360 degrees, no? So take note, we use beta here as radian, not the degree value, but the radian. Okay, mu is of course the coefficient of friction. Okay, so we have here the following notation, no? So beta, so the angle of contact in radian. So take note that if the number of or the angle is given to be, let's say, 2 turns, no? So it's being wound in the uh, roller for 2 consecutive turns, then beta is equal to 360 degrees times 2 and convert it into radian. Okay, so mu is of course the coefficient of friction, T2 is the tight side, T1 is in the slack side, no? So we'll try to illustrate, no? So problem number, or we'll try to illustrate in problem number 14, uh, the concept, no, of belt friction. Okay. So for problem number 14, so we have here a body, no, weighing 500 Newton is being held by a rope. So that passes over a horizontal drum. So the angle of contact is 150 degrees, no? So if the coefficient of friction between the rope and the drum is 0.3, find the least force, no? So means say T1, no? So the slack side that will hold the body. Okay. So the usually the trick in this type of problem is the angle of contact, no? So as I mentioned, so if the rope is being wrap around how many times, then you should consider one rotation to be 360 degrees multiplied the number of times it's being wrapped around. No? So, uh, okay, we'll try to calculate. No? Example number 14. Okay, so in example number 14, so you have there the drum and then uh, the rope, no? So that's being attached. Okay, so 500 pounds Newton, I mean, no, 500 Newton is being attached to this end while this is being pulled, no? So we use a T1. And then the angle of contact in between, no? So beta. So beta, according to problem, is 150 degrees. To convert that one to radian, we multiply it with pi divided by 180 degrees, no? So let's make it 150 divided by 180. So that would be 5 pi over 6. No? So using the formula, T2 divided by T1, so that's equivalent to E multiplied by mu beta. So this is a direct substitution problem. So T1, so that's equivalent to, so T2 is 500 Newton divided by E 0.3 multiplied by 5 pi over 6. Okay. So T1 then can be calculated directly as, okay, so that's 227.96, 97 Newton. Okay, so that's 227.97 Newton. Okay, for the T1. Let's check though. So if we have the 227.97 Newton as the answer, so that's in letter C. Okay. So, and then we are in our last topic, no? So that would be the parabolic cables. Okay, so all of these topics, no, are formula based. That means you have to consider memorizing the formulas or even familiarizing, no, the formulas. Okay, so for parabolic cables, okay, so we can classify it into two, no? So the uneven elevation of support, no? So as illustrated, okay? So, and then we have also the even elevation of supports, no? So for uneven elevation of support, no? So we have these formulas, okay? So T and H, no, represents the tension, no? H is basically the tension steel at the lowest point of the cable. L, so this is the span of the cable, no? Length of the cable, no? So we will be visiting again these formulas now when we solve some of the problems. Okay, so just familiarize now the orientation of the variables. Okay, omega. So this is the load distribution, no? So for the cable. So how do we know, no, that the uh, cable is parabolic? So how do we or what would be the hint, no? So uh, the hint usually for parabolic cable is the word uh, horizontally distributed, or there is the word, no, there is the word horizontally distributed. So for the other type, uh, the catenary cable, no, so the keyword also for catenary cable is the word uniformly. Okay, we'll get back, no, so to the catenary cable. So we'll try to look at the parabolic cable first, no. So the examples are actually separated. So by the way, so we'll try to take a look at the um, parabolic cable first. Okay, for parabolic cable, so we have the uneven elevation of support, no? So this would be the formulas, no? And then the orientation also of the variables. For even elevation of supports, no? So we have this one, no? Okay, so the uh, okay, so this would be the variables, no? So L here, so this would be the span of the cable. So this is actually the length from this point to this point, no? So L is actually the length of this point to this point, no? The horizontal length, okay? So for uneven elevation, so it's being categorized as x1 and x2, no? Since the distance from one point to the lowest point is not the same as with the distance from the other point to the lowest point, no? So L then is equal to x1 plus x2, no? But for the uh, even elevation of support, no? So the distance from this point to the lowest point, the horizontal distance is basically half of the total length L. Okay, so you can see. Might as well the tension, no? Tension for both ends of the cables, no? So are the same, T1 and T2, no? So that's equal to T. Okay, so and then uh, also we can calculate directly, no, the value for the tensions, no. So that would be the tension at the lowest point is given by this formula. The tension at the ends of the cable also is given by this formula. S here is the approximate length, no, of the cable. This one S. Okay. So again, we'll just visit, no? So we'll just visit from time to time the formulas, okay? As we go on with the problems. But for parabolic cable, so one of the hint, no, that gives you an idea if the problem is about parabolic cable is the word distributed horizontally, okay? So from time to time, it will be given in the problem, just like, for example, in number 15. So you have there distributed horizontally that makes this problem as parabolic cable. And then, for example, in problem number 16, so you have their horizontal load, no? So that makes the analysis as parabolic cable, okay? And then the second type, so we will be discussing it later. Okay, so there must be the word horizontally distributed. Okay, so now uh, we have problem number 15. Okay, so for problem number 15, okay, so number 15, so you have or we have here now a cable is supported at points A and B 210 meters horizontally apart with B higher than or with B, no? So 30 meters higher than A. Okay. So the cable sags so that its lowest point is 10 meters below A. Okay, so the uniform load distribution. Okay, so take note, no? So that's distributed horizontally. So that is 400 kilograms per meter. Find the tensions or find the tension, no, at the lowest point. So mean say the variable H. So the cable is not even this one, no, the first scenario. So the elevation is uneven, no? So we are being asked for the value of H. Okay. So first is we try to draw, no? We try to draw the arrangement. So points A and B with B higher than A. Okay, so this would be the cable, no? So this would be point A, cable, and then it sags down and then goes to B, point B. So this would be point A. So point B is 30 meters higher than A, no, according to the problem. So that's uh, 30 meters higher than A. No? So this would be 30 meters. So this would be tension at A. Of course, this would be tension at B. And then this would be H. No? So the tension at the lowest point. Okay. And then other variables. No? So let me go back to the problem. So other variables, no, so includes omega to be 400 kilograms per meter, and then the lowest point is 10 meters below A. Okay, so we'll try to go back, no. So omega is given to be 400 kilograms per meter, and of course, no, uh, H, this one is 10 meters below A. Okay, and another information that we need to know is so the cable is supported at points A and B 200 meters horizontally apart. No? So that means we have, okay, so the distance between A to B, okay, so the distance between A to B, so that's 210 meters. No? So whereas we denote this one, the distance from this one to the lowest point is x1, and then the distance from lowest point to this point here is x2. Okay, so these are the variables that we need. Okay, so we begin by writing the formulas, no? So for uneven elevation of supports, okay, so we can have the formula, no? Try to look at the formula. Okay, so we have here the formula for H, no? So H is basically omega x1 divided by 2d1. Okay, so uh, this one, uh, we denote this one to be d2. No? d1 is said to be 10 meters. No? So according to the formulas, no, so we can calculate h to be uh, omega x1 square divided by 2d1 square, or basically omega x2 square divided by 2d2 square. Okay, so we are being asked to calculate for h, right? But only if we have x1, then we can calculate, no, for h. No? So we also do not have x2. We also do not have d2. No? So, but we also have the formula for t. No? So TA, the tension at A, so that would be the square root of, no? So omega x1 square plus h square. Okay. Whereas tension at B can be calculated as square root of omega x2 square plus h square. No? So these are the formulas. Also, we have the total length that is equal to x1 plus, of course, x2. No? Okay. So only if, no, only if we can calculate, no, the distance, no, the only if we can calculate, no, so the okay. Anyway, we'll try to identify first, no, the variables, no. So d1, that is said to be 10 meters. d2, um, so the height is 30, and then we also have 10, so that would be 40 meters. Okay. So the problem now is to calculate for x1, right? Okay. So we can then calculate, no, h. Okay, so that is omega 400 multiplied by x1, no, square divided by 2 times d1 is 10 square. So this is equivalent to omega 400, no. X2 is said to be okay. We must need to represent x2 in terms of x1, no. So x2 can be calculated as 210 minus x1. Okay, so that's 210 minus x1 square divided by 2 times 40 square. No? So that makes x1 to be the unknown value. No? So we can cancel out. Okay, so we can cancel out 400, 2. So leaving as x1 square divided by 100. So that is equivalent to 40 square is 1,600. So squaring this one, no, so that gives us so you square this one, no, you expand, so that's 210 square minus 2 times 210 times x1. Okay, so remember your algebra. Okay, so plus x1 square. Okay, so try to cross multiply, no? So that gives us 1,600 x1 square. So that's equivalent to 100 times 210 square. That's equivalent to 44,100. Okay, minus 100 multiplied by 420 x1, and then you have there 100 x1 square. Okay, so we try to rearrange this one. Okay, so we have here 1,500, no, x1 square, no? So we subtract 100 from 1,600. Okay, and then plus 42,000 x1. Okay, minus, okay, so that would be 4,410,000. That is equal to 0. So your calculator can solve, no? So second degree, no? So equation. So just go to your calculator equation mode. Okay, and then uh, find the function which can calculate, no, the given variable, no? Negative 4,410,000. So x1 can be calculated as 42 from the calculator, and also x1 is equal to negative 70. So we choose the value 42. Okay, so meaning to say we cannot make use of negative distance. Okay, so if we have x1, then you can calculate already the value of h, no? So for which value is said to be h, that's 400 multiplied by 42 square divided by 2 times. So h can be calculated as 400 times 42 divided by 200. So h is 3,528 kilograms. Okay, so 3,528 kilograms. So we do not use these formulas because we are not being asked for the tension. But if ever, so you just need to recall these formulas, no? And then use the formulas to calculate the tension. Okay, so we have the answer, no? Let me check. 3,528. Okay, so um, let us recalculate again, no? So 3,528 is not given, no, in the um, choices. So let me recalculate it again, no? Perhaps we have, uh, let's recalculate again, no? So, okay, I think we got the mistake, no, from the formula. So instead of d1 square, it's actually d1 only, no? So uh, we got the formulas wrong, no? So that's 2d1, and we also have 2d2 here. Okay, so this makes the solution also erroneous, no? So we try to erase. Okay, so this one. Okay, so it's only over to D1. So 2 times D1 is 10 and 2 times 40. Square is not included in the formula. So I guess we have to recalculate again. Okay, so we have here, or we can cancel out, no? So we can cancel out 402 together with this one. Okay, so leaving us 40 x1 square. That's equivalent to 10 times. Okay, so 210 minus x1 square. No? So basically, we can expand. So 210 square minus 2 times 210 times x1. Okay, remember the expansion, no, in your algebra, plus x1 square. Okay, so and then you can have 40 x1 square. Okay, so minus 10. Okay, and then plus 10 times 2 times 210. Okay, and then minus 10 times 210 square. So that would be 0. Okay, so we can reduce this one to 30. Okay, so plus we'll have 10 times 2 times 210. So that's 4,200 x1 minus 210 square. No? So that's 44100. So x1 can be calculated. Again, go back to your equation mode, no, in your calculators. So we can have x1 to be 70, and the other one, our calculator will give you negative 210. Of course, we discard, no, so this value, and then calculate for h, I mean, no, so h would be, so omega 400 multiplied by 70 square divided by 2 times 10. So we have here 400. Okay, so divided by 20. So this gives us 98,000 kilograms. Okay, so 98,000 kilograms. That's okay. We'll try to take a look if we have the 98,000 kilograms from the choices. Okay, so that would be, there you go. That's letter A, no? Okay, and then we proceed, no, to sample number 16. Okay, so for example, number 16, so you have the cable carries a load of 20 kilograms per meter. No? So neglecting its own weight. Okay, so the maximum, take note, is horizontal load. No? So find the maximum tension on the cable if the distance between the support is 100 meters and the sag is 5 meters. So uh, in problem number 16, it's very clear, no, that the cable is or the cable has, no, the supports to be even, no, this one, the scenario would be this one. Okay, So we are being asked to calculate for the tension. Okay, so find the maximum tension, no? That is the T, this one. Okay, so we'll try to draw the equivalent diagram of this one. Okay, so we have, okay, so we have, okay, number 16. So let's go back to, okay, so this is for number 16. So the cable is parabolic, evenly supported. Okay, so the load, no, so is 20 kilograms per meter. So the distance between support is 100 meters, and the sag is 5 meters. Okay, so omega here is 20 kilograms per meter. The sag, okay, so this one to the lowest point is 5 meters, and the distance, horizontal distance between the cable is 100 meters. Okay, so uh, we are being asked to calculate for the tension. No? So we begin by writing the formulas. No, that is okay. So that is H. No, so we have the tension here, the same tension, and then the tension at the lowest point to be H. So we begin by writing H to be omega L square divided by 8B. Tension on the other hand, that is square root of. Okay, so that's omega L square, okay, plus H square. Okay, so we begin by writing the variables. L is equal to 100 meters. That's the distance between the supports and horizontal distance. D is 5 meters. Okay, and uh, okay, other variables. I think no. So we have already omega. Omega is 20 kilograms per meter. So we can calculate directly H, no, to be 20 kilograms per meter divided or multiplied with 100 square, 8 times 5. No? So this gives us 5,000, no? Kilograms. T, on the other hand, so that is equivalent to uh, 20 multiplied by 100 divided by 2 and then square plus 5,000. So T here is equivalent to we have here 5,099.02. Okay, so that is kilograms. No? So we'll try to take a look at the choices. No? Okay, so that would be, we'll try to take a look at the answer. No? If it is in choices. No? So that's 5,000. Okay, that's in letter B. Okay, so that's 5,099 kilograms. Okay, so the next topic would be the last topic, no? So for statics, so we will be solving catenary cables, no? So the situation, no, of catenary cable is different, no, so to that of the parabolic cable. Okay, so let's um, proceed, no. Okay, so the last part, no, so we have the catenary cables. Okay, so if you have the parabolic cable and then the hint, no, so that the analysis would be a parabolic cable. So we have the horizontal load distribution for catenary cable. So the hint, no, that you'll be analyzing it using catenary table is, of course, the first one is the absence of the word horizontally distributed, or the term must include uh, its own weight, no, so that's considered to be catenary cable, or you have their distributed along the entire length, no. So let's try to take a look at example number 17, for example, no. So a cable 60 meters long weighs 1,500 Newton. So the tensions at the ends of the cables are, so how far is the lowest point below the lowest end? So in this case, we analyze this one using the catenary cable because the first hint is the absence of the word horizontally distributed load. And if we try to analyze further, the cable, okay, the load of the cable is its own weight. Okay, so try to take a look. A cable 60 meters long weighs 1,500 newtons. So meaning to say that the weight that is being carried by the cable is its own weight. No, so that's catenary. Okay, and then also in number 18, so a wire weighing 0.5 pound per foot is stretched between two parallel supports, two level supports. No, so if the sag is 40 feet, determine the maximum tension. So try to take a look at the given statement. So the wire weighing, so it's the weight of the wire. No, so for parabolic cable, that is, there is actually a load, no, so that is being placed, no, in the what I mean the cable, no, so that's horizontally distributed load. But for catenary cable, it's actually the weight, no, so of the cable, uh, its own weight, no. So that would be the hint, no, so that we uh, how are we going to solve or analyze the problems involving cables. So would it be parabolic or will it be catenary? So as you can see in a catenary cable, so the first um, scenario would be the uneven, no, elevation of supports. No, so as you can see, so we have T. So this would be for tension. So Y. So this would be the distance, no, from the end of the cable to the reference ground. Okay. So the distance from the lowest point to the reference ground is denoted by C. So and then we have these variables, no, or equations that we can use, no, to calculate unknown variables for catenary cables. Okay. So all you need to do is to, of course, rumble all these formulas, no. So or if the problem, no, produces direct substitution, then the better, no. But then if it will involve, no, a lot of variables, then you have to juggle up all of these formulas. Okay. So x1 and x2, so would be the still the horizontal length, no, from one end to the other end. Okay. So, and then we have the second type, the even, no, even elevation of supports. So as you can see for even, so the variables are symmetrical. Okay, so tension T, that would also be the same tension, and then the length of the cable S, this one, no, so it's also half, no, of the entire length S. And then instead of x1 and x2, so we have here length over 2 and length over 2. And then we have here the formulas, no? Okay, so well, it's up to you, no, on how are you going to memorize these formulas. But one way to do so is to keep on, well, practicing, no? Solving problems, and then uh, you will be familiarized, no, so with the formulas. Okay, so okay, let's try to take a look at number 17. Okay, so number 17, so we have here a cable, so that's 60 meters long, weighs 1,500 Newton. So the tensions at the ends, no, of the cable are 1,500 and 1,650, okay, respectively. So how far is the lowest point below the lowest end? Okay, so we are being asked, no, so to obtain how far is the lowest point below the lowest end. So basically, we are being asked to obtain this distance, no? So this is the lowest end, and then this would be the lowest point. So this would be the distance, no? So that is being asked. So we denote this one to be, let's say, h, no? So what would be the distance h? So that is equivalent to y2 minus c. So of course we need to calculate y2, and then we need to calculate c. Okay, so uh, okay. So how are we going to calculate this one, no? Okay, so we'll just use this empty portion here. Okay, so in order for us to look directly, no, the formulas. Okay. So according to the problem, T1, so this is the tension, no, at the highest point. So that is 1,650 Newton. T2 on the other hand is also 1,500 Newton, no? Okay. So by formula, we can calculate omega, by the way. Omega is equal to the length, 1,500 Newton, divided by the entire length, 60 meters. So that makes us, or that will give us 25. Okay, so that gives us 25 Newton per meter. Okay, so we then calculate T1, so that's equal to 1,650. That's omega Y1. So Y1 can be calculated as 1,650 divided by omega, that's 25, 66, no? So that's 66 meters. And T2, okay, on the other hand, so that's 1,500. Okay, that's omega Y2, no? So Y2 then is equal to, okay, so that's 25, that's 60 meters. Okay, and uh, as I've said, no, so our objective is to calculate, no, the value of C, no? So such that we can calculate the distance from the the lowest point to the lowest end, no? So how far is the lowest point to the lowest end? So this one, the variable age, I mentioned a while ago, no? So this one, age, small letter h. Okay, so well, you can use any variable. So in this case, I use h, no, so as the height between T2 and h. Okay, so next is to find a variable c, no. So okay, how are we going to calculate for c? So we didn't say, no, we didn't say that the total length. So that would be S1 plus S2. So that would be 60 meters long. Okay. So we have formulas here. Okay. So you have the Y1, this one, no? So we'll use this one. So Y1, so that's 66 meters square. That's equivalent to S1. Of course, square plus C square. Okay. And also we have this formula Y2, no? So that's 60 square, that is equivalent to S2, that's 60 minus S1 square plus C square. Okay, so this would be equation number 1 and equation number 2. So all we need to do is to subtract equation 2 from equation number 1. Okay, so to eliminate C, okay, to eliminate C square. Okay, so this would be, or this will give us, no? So that is 66 square minus 60 square. That is equal to S1 square minus 60 minus S1 square. So C square will be cancelled out. So calculating directly, so or this gives us 756, no? So this is S1 square minus, no? So 60 square is 3,600 minus 2 times 60 times S1 plus S1 square. Okay, so this gives us 756, no? So that's S1 square minus 3,600 minus 2 times 60. Okay, plus. Okay, so because of this negative value, no? So multiplied by S1 minus S1 square, no? So we can cancel out S1, as you can see. So this gives us value, no, for S1. So that's 756, no? So plus S1, not S1, but 3,600. Okay, so that's equivalent to 120 S1. So giving us S1 to be so 36.3 meters. Of course, we can calculate C after. Okay, so calculating for C would give us, so let me erase this one. Okay, so we have there 66 square, that is equal to 36.3 square plus C square. Okay, so C then is equal to, then this gives us 55.12 meters. So the variable h, no, so can be calculated as h, that would be y2 minus c. Okay, so y2, that is 60 meters minus c, 55.12 meters. So this gives us 4.88 meters. Okay, so 4.88 meters. So let's try to look at if we have the, okay, that's letter A. Okay, so that's letter A. That's 4.88. So that's 4.88. This one. That's 4.88 meters. Okay, so that is for item number, okay, number 17. No, so that's for item number 17. Okay, so well, other formulas may be used, no? So depending on what is being asked, no, in the problem. So sooner you will encounter some of these, some problems involving like this. Of course, you have to familiarize, no? So you have to be familiarized with the formulas. Okay, this one. And then the last, no, the last problem. Okay, so we have here, no, so the um example number 18. So a wire weighing 0.5 pound per foot, no, so is stretched between two level supports, no. So it's the weight of the wire, so therefore it's catenary, no. So the sag is 40 feet. Okay, so determine the maximum tension. So we're being asked for the variable T, this one. Okay, so uh, perhaps we can make use of this portion here again. Okay, so for us to be able to see directly the formulas. Okay, so okay, so for problem number 18, no, so we have catenary cable, so with even, no, support. Okay, so as mentioned, omega is given to be 0.5 pound per foot, no, as given. So stretch between two level supports. So the distance here, L, this one. So we have there L is equal to 160 feet. Okay. So the sag is 40. So distance here, 40 feet. Okay, so we are being asked to calculate for the maximum tension. Okay, so for the maximum tension, we'll try to look at the formula. Okay, so T is equal to omega Y, and of course, H is equal to omega C. Okay, so omega Y and omega C, no, for H. Okay, so we'll have it, the tension, T. So tension, and then the tension at the lowest point is H. Okay, so we'll try to uh, make direct substitution, no, if it's possible. But if not, then we have to use the other formulas. No? So T, that is equal to omega Y. Okay, but are we given with the Y? Let's try to take a look at the diagram. Y is the distance between the end to the level ground. No? So we're not given with Y. Also, we're not given with C. Okay, so I think this is not a direct substitution problem. Okay, so this would be Y, and of course this would be C. Okay, so omega Y, and of course H is uh, we do not have also the value for h, right? So what are we going to do is to uh, write t, no? So t that is equal to omega is 0.5 y, okay? And also h, that is omega c, no? So h is equal to 0.5, okay? So multiplied by c, okay? So um the sag, no? So the sag is 40 as given, no? So that is we can calculate this one as 0.5. C can be written as y minus 40. Okay, so such that we can have y variable for um, equation 1 and y variable also for equation number 2. So our objective is to find a way, no, wherein we can calculate for y. So if we have y, then of course we can calculate directly for the tension, no? So okay, other formulas that needs to be used, no? So we have here this formula, no? So uh, this one, no? So y square that is equal to uh, s over 2, no? Square plus c square. Okay, so we have this relationship, no? Okay, and then uh, we also have x, no? So that is equal to c ln of s over 2 plus y over c. Okay, so okay, so this would be uh, a bit tricky, no? So we are not given with the okay, so I think we need to find a way, no? So we can calculate, no, for the uh, value of c. Okay, so we'll try to use the other formulas. Okay, so these two formulas here. Okay, so y square. Okay, so we can have uh, okay, so we can make use of this formula here, no? So y square, that's equal to s over 2 square plus c square. Okay, so using this one, so we can proceed with, no? So okay, so we'll write it down. Y is also already okay, so this would be y square. So this is s over 2 square plus c square. Okay, c is y minus 40, right? Okay, so such that we can calculate y. Okay, so that is um okay, y square, that is s square over 4. Okay, so plus y square minus 2 times 40 times y. and then plus 40 square. So we can eliminate y square. Okay, and leaves s square, no? So we can, okay, so that gives us for a while, no? So let's, okay, so we can have here, instead of simplifying s over 2, so perhaps you can just simply write, so we can just write here s over 2 square. Okay, so that would be plus. So we can have s over 2 square. So that's equal to 480 y minus 1600. Okay, so or basically we can have, if we continue here, so we can have s over 2 that is equal to square root of 480 y minus 1600. Okay, that is the value for, or the value of s over 2. Okay, now still we cannot get, no, the value for y, because here comes another variable, no, so which is s over 2. Now if we try to take a look back at the formula presented a while ago, no, so this one, the fourth formula, so we have x equals to c ln of s over 2 plus y over c. So x here is actually the distance between, the horizontal distance between one end, this end, to the lowest point, no? So which is equivalent to L over 2, right? So therefore, we can make use of this formula, this one. So if we write the formula, like, uh, if we erase this one, okay, so we'll just erase this one first, no? So we have already identified what is S over 2, okay? So we write the formula, okay? So this is x, no? So that is x is 160 over 2, no? So this is 160 over 2. So this is actually x, okay? So that is half of the uh, horizontal distance, no? Because that's even, the support is even. That is c. So c, on the other hand, is that is y minus 40, and then ln of, no, so that's ln, no, so of, so s over 2, so that is square root of 480 minus y, I'm sorry, that's 480 y, okay, 480 y minus 1600 plus y divided by c. C is y minus 40. So this time, the only variable left in the equation is, of course, y. Now, because of the complexity of the equation, so we just need to use the shift solve function in our calculator, no? Okay. So all we need to do is to use the shift solve function. Okay, so to use shift solve, no, so I have here a virtual calculator. Okay, so we can have, no, so we can calculate, we can use the shift solve function. So that is x, no, so that's 80. So that's 80. Okay, so you type this one in your calculator. That is c. C is y minus 40. No, so we can denote y as x. Ln of. So s over 2 is square root of uh, that's y square minus, okay, so okay, so that's the formulas are gone, no? So that's y square minus okay, so that's 400, no? I think that's square root of, okay, let me check. So the formula for is y square, okay, so that's okay, so okay, and then you have there uh, okay, so let's go back to the calculator. So ln of um so s over 2 is given to be square root of, okay, that's 80, no? 80, so 80, and then minus 1,600. Okay, and then plus the variable y. Okay, and then divided by c. No, c is y minus 40. No, so okay, so to solve, use shift solve function. So we are given with the variable y, no? So the variable y to be 125.94. Okay, so 125.94. Okay, so uh, we can now calculate, no? So we can now calculate for 125.94. So we have here the tension, no? So tension, that is omega y, no? So that is omega is 0.5 times 125.94. So tension would be 0.5 times 125.94. That's 62.95 pounds. Basically, approximately equal to 63 pounds. So this would be the answer, no, for item number 18. Okay, so now if you want, no, if you want to uh, have, no, so more practice problems, you can refer, no, you can refer to some review books available. Okay, so there are a lot of review books available, no, so in the market. Okay, so you can also uh, buy it, no, so from our store. So you can visit, no, you can visit us at uh, room 401, CDC building. So Barangay Santo Niño, Osmeña Boulevard, Cebu City. That's actually in front of Santo Niño Church, above Jollibee. You may also opt to order it via COD. Okay, so you can buy it from uh, this account. Just search okay, so that's Mrs. Jenny Bayon. So you can order us via COD. Okay, so that would be for the topic uh, statics. No? So you want to dig further, so you can have this book, the blue one, together with the uh, objective. No? So the terms for engineering sciences. So we have the corresponding book, no, for the objective questions. So for mathematics, we have this one. For master electrician, we have this one. For electrical engineering subjects, we have this one. Okay, and this would be the terms, no, for electrical engineering professional subjects. Okay, so please do not forget to share and uh, might as well like and subscribe to the page.